we have a program today, which is good. It's an unusual program. To paraphrase Mark Twain, everyone talks about space weather, but no one does anything about it. But having advance warning about big hurricanes and cyclones and tornadoes and flooding is vital to help us prepare for disaster and for longer term things. Space also has intense weather. Dr. Dan Baker is the director of the Laboratory for Atmospheric and Space Physics, which until very recently I never knew what LASP stood for when I read it, but now I know, which is, enlightens me a bit. He's joining us today to explain how space weather affects our lives and affects the complex technologies that we use in our lives each day. Dr. Baker, welcome to Boulder Rotary.
Thank you very much. Let's see if I can get wired up here. See if this works. Is there an engineer in the house?
Several.
A little hard to see from this angle. No less a personage than Rush Limbaugh took me to task by name on his radio show. Mr. Limbaugh said, "We can't even predict weather on Earth." And here's this guy at the University of Colorado named Daniel Baker who thinks he can predict weather in space. I regard it I have it as a badge of courage and honor that I've withstood the attacks of Rush Limbaugh, and still I'm working on this topic. This figure is a fraud. The picture you see behind is a picture of the sun in soft X-rays. The counter picture of the Earth is in visible light. The Earth is nowhere near as large as that compared to the sun, and the Earth is not that close to the sun, otherwise we'd all be dead. But the point of this picture is to talk about two things. One is the sort of upper trace there that represents the work that I've done for much of my career. It's really to study the sun, to study the magnetic field and environment around the Earth and understand the relationship between them, to apply those lessons to other planetary systems, and to extend our understanding then to the plasma universe beyond. The lower trace, the lower branch of this, is more the topic of today's conversation. It's about the effect of the space environment on humans in space, on spacecraft operating in and around the Earth, about the effects on human technologies such as power and communication, and probably even effects on the climate of the Earth. So I wanted to first introduce to you, of course, many of you know that the Earth has a magnetic field. This magnetic field emanates from the molten core of the Earth. It's largely a magnetic dipole, or there are higher order moments which would be important given what I'm going to talk about. But the magnetic field is due to the rotation of the Earth and to the dynamo action in this molten core. This gives rise to a region called the magnetosphere, an extended tail, a comet-like tail that extends for thousands of Earth radii, also a standing bow shock wave. And this envelope, this region is called the magnetosphere. And much of the magnetopause surface protects us from the inflow of the solar wind, the gases from the sun, and many of the cosmic rays that come from deep in our galaxy. This region also houses cold gases, what we call plasmas, the extraterrestrial ring current, which is very energetic ions, and then the Van Allen radiation belts that are even more energetic. If it weren't for this magnetic field, it's doubtful that life as we know it would have evolved on Earth. It's very protective. It's an umbrella under which we hide. And the energy that from the sun occasionally can penetrate through this boundary and can drive what we call powerful geomagnetic storms. And so the interplanetary field from the magnetic field from the sun can interact with the Earth's magnetic field, open a gate, allow energy to flow in, and this can give rise to powerful storms, what we call geomagnetic storms or magnetic storms. These can release huge amounts of energy, which can flow down, typically in the kind of field configuration we have now, into the polar regions, giving rise to enhanced energetic particle populations that affect all kinds of things, as I'll talk about, but also can flow down and form the aurora that have fascinated humans from time immemorial. And seen from above, this is like a TV screen on which things are projected. Seen from below, we have these fascinating auroral curtains. So space weather, as the president just said, who knew there was space weather? But people have certainly commented on weather for a long time. Oscar Wilde said conversation about the weather is the last refuge of the unimaginative, which I think is sort of true. On the other hand, Ken Hubbard, the American humorist, said, don't knock the weather. 9/10 of the people couldn't start a conversation if it didn't change once in a while. And that's true about space weather as well. But the authorities have spoken, and space weather is then the term that refers to effects on human technology, potential devastating effects, disrupting effects on the power system, on satellites, on aircraft, on all the technologies on which we rely. Now, the sun is the primary driver of space weather, and the effects vary over time. The sun has an approximate 11-year sunspot cycle. I heard Joanne Jocelyn's name mentioned. She's probably talked to this group before about that. Why the sun has an 11-year activity cycle, not a 20-year or 5-year cycle, isn't really known. But these pictures in soft X-rays show the sun going from very active to being relatively quiescent and undisturbed, and then back to an active cycle. Right now we're in the very low period. But if we look in again, sort of the X-ray wavelengths, we see the sun can have these bright active regions. They can spew out large blasts of material called coronal mass ejections, can produce huge fluxes of charged particles that blind essentially the imagers in space, as you see there. This is more of an artist's concept, but something, we don't know exactly what, but sometimes there's a loss of stability on the sun. Material blasts out from the sun. Perhaps 10 billion tons of material moving out at, let's say, 8 or 9 million miles an hour, rapidly progressing from the sun, going the 100 million miles, 93 million miles to the Earth. Now, I know many of you in the audience are interested in the Earth's magnetic field. You see here this interaction which gives rise to powerful storms. If we didn't have the dipole field, then there would be much freer access of this energy to all parts of the Earth rather than just the polar regions. And this is one of the things I wanted to mention to you, is that there's a lot of question, a lot of speculation about whether the Earth is undergoing now a flip in its magnetic field, whether that dipole field is going to diminish substantially and we'll have only the higher quadrupole and octopole moments, and whether in fact, this kind of disturbance that we're talking about here might have much more ready access to the Earth's lower latitude regions where we all live. So again, imagine this blast coming but not having this protective umbrella there, and that's something we can talk about during the course of this brief lecture today. So there are literally thousands of spacecraft in orbit around the Earth. Right now there are about 2,000 active satellites. Many of our technology leaders have plans to put many, many more satellites into orbit. There are, as I say, about 1,800. About half of those are in low Earth orbit now. We're going to probably get hundreds or thousands of new ones from Elon Musk and other technology leaders who are going to then have to deal with the challenges of possibly a lot of space debris. So this is an illustration from a paper some time ago, just talking about that there are many effects on any satellite in space. There can be effects due to high energy particles from the sun. There can be large effects from Van Allen radiation belt particles, and there can even be effects from lower energy particles that are produced in what we call magnetospheric substorms. And so these kind of effects can be devastating. Just to motivate this, just at the one key satellite location, the geostationary orbit, about 22,000 miles above our head, there's a place where spacecraft rotate around the Earth about the same speed as the Earth turns, so they appear to stay above 1 point above the Earth's surface. That's called geostationary orbit or geosynchronous orbit. There are hundreds of spacecraft there, and this is an old picture, 10-year-old picture, but there are estimated to be multiple hundreds of billions of dollars of assets of civilian satellites just in that one location alone. So there are many new drivers for concerns about space weather. This shows some of them. Probably many of you use the GPS system, so generally known as GNSS, for positioning, that there is increased planning for using space for the next generation air transport system. The vulnerability of the power grid is something that I'll touch on briefly here. The increasing commercial satellite industry, intense new plans for exploration to the moon and beyond with humans, commercial space enterprise, Arctic exploration, and so on, many, many things. This is a diagram from Fugro Chance just showing some of the applications that they have for the GPS. This went from being essentially nothing in the mid-'80s to now being approaching $1 trillion business, just the application of the use of the global positioning signals for all kinds of things, positioning, surveying, construction, and a whole host of other uses. And this is extremely important going into the future, and space weather can affect this very seriously. One way that this can affect is that the plan has been to use the wide area augmentation system for airplane flights. The system used to be one of having all these kind of ground stations, say over North America, to provide signals to aircraft. Using GPS was viewed as the be-all and end-all to really improve the system. But here's a diagram. In this, blue is good, red is bad. It's really an indication of the amount of electron content through the integrated and height above the atmosphere. During one powerful geomagnetic storm in very short order, the whole system became unusable. This was back in October 2003, and remained unusable for about 30 hours, so that you couldn't really use this GPS-based WAAS system. Instead, the system was incapacitated by a powerful geomagnetic storm. Space weather can have other effects. Bright X-ray flares from the sun can blind high-frequency radio communication on the entire sunward side or day side of the Earth. And we still use high-frequency radio communication for airplanes and many other applications. And so this kind of immediate effect from a solar disturbance can be pretty significant. Another use, and this is very pertinent to the changing magnetic field, but I just flew back last night from Dubai, a fairly high latitude flight, not quite this high latitude, but there are many flights from North America now to China, to Asia. And the airlines that fly these high latitude routes have to remain in radio communication. If there is a powerful geomagnetic storm, or more particularly a powerful solar storm, if you can see this is looking down on the North Pole of the Earth. The entire region shown in red here is where very powerful solar particles can funnel down along the Earth's magnetic field and can essentially black out radio communication over that entire area, necessitating flights at lower latitude at much greater cost. Again, if the Earth's magnetic field ceased to be mostly dipolar and became weakened, then these particles could have influx essentially over the entire Earth surface, could be producing similar kind of disturbances all over the place. Now, human spaceflight, of course, is of increasingly great attention to policymakers and to the public. The plan is to go from flying around in circles, you might say, in low Earth orbit with the space station to going back to the moon and Mars. And the space radiation has dramatic effects even on the space station, would have more so if for long duration flight to the moon, and especially going to Mars, for example. I was privileged to chair for the National Academy's study looking at the space radiation hazard. This is from a decade and a half ago, but it's still very relevant. This report speaks about many of the possible consequences for space radiation. This lists some of them. Here you see attention possible cancer-causing effects, degenerative tissue effects, damage to the central nervous system, acute risks. Death is a bad acute risk, I guess. But vomiting inside a spacesuit, even the new spacesuits that are highly touted now, could be a very life-threatening thing, either on the surface of the moon or on the surface of Mars, for example. So these kinds of risks of space radiation are very well established. Probably one of the major concerns that we have should be really the effects that this can have on such things as the power system. Again, I was privileged to chair a committee for the National Academies looking at the societal and economic impacts of severe space weather. I guess that was the title that I originally gave for this talk. And we brought together experts from many of the different disciplines, many of the different areas of government, industry, academia, to talk about this. But many of the things I've talked to you about are recognized as a hazard. Now, policymakers may have hazard fatigue, just worrying about all the different things that can affect society. But this is one of the most likely, I would say, of the hazards to affect large portions of the Earth's surface. And the power grid is particularly a sensitive issue, as has been demonstrated by Superstorm Sandy and many other recent events of terrestrial weather. The loss of electric power can quickly spell the loss of the ability to pump oil and gas, to provide transportation, to have potable water, to have effective emergency services, and so on. So these connections are substantial and very significant. And the loss of electric power for even a few hours is an inconvenience. For a few days is a challenge. For weeks or months or even years could be a huge effect. And the electric power grid is increasingly sensitive to the possible effects of space weather. We have a power system in North America that's decades old, transformers that may date back 50 or 60 years. And the possibility of an effect in one region that can cascade through the connected power grid over much of the continent would be a very severe matter. Another study that I think is one I cited before has looked at this, and under the right circumstances or the wrong circumstances, there could be a very extended outage of power over large regions and could lead to economic losses extending into the trillions of dollars. When we wrote this report, $1 trillion was a lot of money. I'm not sure that that's true anymore, but maybe it is. So what about addressing space weather then? Again, the sun is a principal driver here. Coronal mass ejections, as I talked about, can be these powerful blasts of material, if directed toward the Earth, could produce very significant effects. The impacting of these powerful solar effluents onto the Earth can lead to the outages of power, as I've mentioned. We've had examples of this in numerous instances. But the major effect here is one of coupling energy from this rapidly flowing, powerfully flowing solar wind down through the protective envelope of the magnetosphere down into the polar regions. These currents can couple into long conductors like pipelines or the electric power grid, long run cables. This can lead to power outages such as occurred in the Montreal, Quebec instance in 1989. We've had much more powerful storms than that have just missed the Earth, I'd be happy to talk about. But these storms can also produce outages, as I mentioned, in the high-frequency radio communication relying on ionospheric effects. Also, the ionosphere is the system through which signals from GPS gets transmitted, and so a loss of signal for the GPS can mean that we're affecting precision agriculture, navigation at sea, and the countless other applications that we now have for the global positioning system. In space, space weather can affect constellations of spacecraft. It can affect the individual spacecraft through effects on the sensitive electronics within the spacecraft or the power cells. And as I've mentioned, it can even affect astronauts on the International Space Station, let alone when they're outside the protective envelope. So I'd say that solving the space weather problem relies on us having core kind of modeling capabilities, also key observations and the kind of knowledge and wisdom to apply this to understand the sun and the consequences near Earth. I think it is within reach for us to make substantial progress on this problem. I think we already have. Talking to John earlier, we've gone from very few people knowing about space weather to many policymakers now having elevated this to the other kinds of hazards like earthquakes, floods, and so on. So let me summarize and leave some time for questions, but I'd say that the challenges of space weather affect all developed and many developing countries, both civilian and military systems. Work on space weather specification, modeling, forecasting has great societal benefit. I like to call it basic research with a high public purpose. Future space exploration and most modern human endeavors, as I've tried to indicate, will require that we have major advances in our understanding and improved transition of research knowledge to more operational capability. And then how do we deal adequately with what's very real space weather threats, especially if, as I say, another confounding factor in this might be that the Earth's magnetic field seems to be changing rapidly now. And were the magnetic field to go from this well-developed and obvious strong dipole to a more fragmented kind of quadrupole or octopole kind of field that's characteristic of these flip times, how would we as a society be able to deal with that? So with that, I'd be happy to answer any questions, and thank you very much.
Is Mercury going into retrograde a real thing, and is that basically what you're talking about with the solar flares and things?
Mercury?
The term, when people say Mercury went into retrograde, my electronics don't work.
I don't know. I've studied Mercury, but I don't know how that really plays. I'm sorry, maybe we can talk afterwards offline and I can understand the question more deeply.
Hi, thank you so much for your talk. What can you tell us about the correlation between solar flares and the increased rate in suicide and psychotic episodes? Has that been sufficiently researched, or?
The answer is I don't think it has been sufficiently researched, but I know that many of our Soviet colleagues back in the late 80s and early 90s, I know had been studying that quite extensively. And to me, it's rather amazing all the biological systems that are affected by these powerful storms, the magnetic field changes, and the increased activity levels. And so, things that may seem unlikely or that the connection isn't obvious have actually been studied and have been found. Now, we know that there are many biological systems that are very sensitive to the changing magnetic field, for example. John Jocelyn, as I say, may have spoken here about homing pigeons and the effects that, and all the animals that rely on magnetic signals in order for their orientation and migration and so forth. But as far as has it been proven that there's an increased correlation, say, between geomagnetic storms and psychological issues? I don't think that's been well enough established.
So the magnetic field has changed before, has it not? And
yes.
How far is it going right now, and what happened the last time it
Well, there weren't a
flipped?
lot of humans around when it changed before, and so the effects on technology were pretty marginal, but the flips occur on timescales of roughly tens of thousands to perhaps 100,000 years or so. And these have been well documented in the magnetic materials in the ocean floor, for example. You can just look back, read it almost like a book, to look back and see when the changes in the magnetic field have occurred. When the magnetic field has reduced, it appears that there can be much more influx of cosmic rays, as I say. There can be effects that are recorded in other long kind of isotopic records and so on. What's fascinating now is that the Earth's North Pole has been migrating at a very rapid rate. It's been moving from where it was in sort of Greenland toward northern part of Canada. We have many military systems, many civilian systems for that matter, that use the position of the pole for their guidance, and so we have to have much more frequent kind of observational updates to magnetic models in order to be able to assure that the systems that we have that are dependent on magnetic field orientation are well suited for the times. And more broadly, if the things that are happening now are indicative of the Earth moving toward a magnetic flip, which is essentially an effect in the dipole, where the dipole component is greatly reduced, then we have this whole host of things that I was talking about in this set of brief remarks, that we would have much different situation, much more ready access of solar and galactic cosmic rays, for example. All of the things that we've based our navigation on would be thrown into disarray by such a change. Now, this isn't going to happen overnight. These kinds of things probably take 1,000 years or more to undergo sort of a full flip, but it would be an interesting 1,000 years to be around.
You said that
Yes, sir.
you said that the fields that surround the Earth are necessary for life as we know it. To what extent is there an understanding of those fields that are necessary to life in the universe?
Yeah, little is known, of course, about life elsewhere, but this is I think this is one of the important speculations, is that not only when I'm very proud that LASP, for example, was the mission operations site for the Kepler mission, and we found 4,500 new planets around other stars. 2,500 of those have been confirmed as other planetary bodies. And one of the things you look for, of course, would be evidence of an atmosphere that could sustain life. But now I think there's more appreciation that another factor that we should really be looking for is evidence that there's a magnetic field to help provide this protective envelope. We look at Mars, for example, which started out as a warm, wet planet 4 billion years ago, 4.5 billion years ago. Over the first billion or billion and a half years, because of its interaction with the solar wind, because it lacked a strong magnetic field, the atmosphere has been scoured away. So just in our own solar system, we see evidence that this magnetic field that stands off the flow of the solar wind plays a very important part in maintaining a habitable environment. In other planetary systems, it's presumably the same situation, that you'd want to have this magnetic field to help stand off the stellar wind flow. You'd want to have it there to prevent too much cosmic radiation from killing life before it even got started, all these kinds of things. So whereas I'm speculating a bit, I think it's a widely held view that the keys to having life, as we understand life, would be to have a relatively warm or relatively wet environment, one that's protected from the onset of this kind of degradation that's associated with the solar wind flow, protective atmosphere that keeps away the intense X-rays and gamma rays that form in the stellar flares, and keeps the galactic cosmic rays at bay. So all of those are factors that I think need to be considered. And I think it's something that as we start to look more actively for other habitable worlds, we'll want to look for signatures like auroral displays and things like that, if we can see them, that indicate that there's really a magnetic field at these other bodies as well.
Yeah, first of all, I want to thank you for giving me something else to worry about.
Yeah, you're welcome. Yeah. There's no extra charge for that, by the way.
So, as I said, that all the planets in our solar system do not have this. The other planets, we're the only one.
Mercury is a small planet, but it has a relatively strong magnetic field. Venus is very Earth-like, but has no magnetic field, no global magnetic field. Mars has regional magnetic fields, but no global field. Jupiter, the gas giants all have magnetic fields, but they don't have the surface or the kind of habitable environment. So what we're looking at for habitability is sort of the Goldilocks zone, to be in the not too warm, not too cold kind of thing, and to have all these other properties. And the Earth is our particular example of a place that's just about right for life to start and to be sustained. Going back to the other question, I guess what we really would be looking for would be this whole set of similar situations at other worlds beyond our own solar system, and see whether this would exist. But yes, I think even in our own solar system, the various moons that might be thought to harbor life or so would be quite different from what we understand, probably in the large oceans under Europa, or possibly Enceladus or something like that. But I'd say it's fairly far-fetched. Mars may have had life at one time. Yeah.
Dr. Baker, I just want to thank you so, so much for coming to speak to us today.
Thank you.
As a huge space nerd, I can only say thanks. And I'm also grateful to the Earth once again. It's given us a lot. So in your honor, and to say thank you for giving us your program today, the Boulder Rotary Club is going to donate 100 vaccinations to the Polio Plus Foundation, and we really, really appreciate it.
Thank you very much. Thank you.